Hi, this is Mrs. Villette, and this video is to go over complex rational expressions. To start off with, we need to have a definition of what a complex rational expression is. So a complex rational expression is the ratio of two or more rational expressions. We need to remember that a rational expression is already a ratio of two polynomials. So a complex rational expression is a fraction where either the numerator or the denominator also contain fractions. If we look at this first example here, this is a complex rational expression that only involves numbers. So we have the fraction bar here, but then above the fraction bar we have a numerator that is itself fractions and a denominator that is fractions. In order to simplify a complex rational, there are two methods. So the first method, or method 1, is we are going to multiply by something that's equivalent to 1. We're going to choose an expression that is of the form the lowest common denominator over 1 divided by the lowest common denominator over 1. Notice that this is the same thing in the numerator and the denominator. When I say numerator and denominator, I mean the part above the large fraction bar. And so that is an expression equivalent to 1. And we will be fully simplified when the numerator and denominator no longer contain any fractions or common factors. Let's take a look at how it works with numbers. So this first example, we have a third plus 2/5 over a third plus 2/9. So we need to find the overall lowest common denominator. So the overall lowest common denominator, we're looking at the LCD between 3, 5, 3, and 9. So those are all four of my denominators. You want to think about if you were trying to add these two fractions or four fractions together, what common denominator would you use? And in this case, we would use 45. So we are going to multiply this fraction by 45 over 1 over 45 over 1. So it's really like we're multiplying by 45 over 45. Go ahead and distribute, and you get 45 over 3 plus, I'm going to write this as 45 times 2 over 5 instead of 90 over 5, and you'll see why in a minute. And then I have 45 over 3 plus 45 times 2 over 9. Now we go through and we reduce. 45 divided by 3 is actually just 15 over 1, or 15. Here I can do 45 with 5 and get 9 times 2. 45 over 3 again is 15. 45 divided by 9 is 5, or 5 times 2. So now I have 15 plus 9, oh, not 9, 15 plus 18. Over 15 plus 10. And we simplify to 33 over 25. Notice we can't cancel until we have fully simplified the numerator and the denominator. And simplifying in this context means combining the like terms. So 33 over 25 does not reduce any further. Now, one thing that you could do is simplify as you're multiplying. So you could recognize that 45 and 3 have a common factor of 3 and just write 15. 45 and 5 have a common factor of 9, and then 9 times 2 is 18. Probably would be a good strategy right here to go ahead and write that this ends up being 18, and this whole thing ends up being 10, so you don't forget that. Let's take a look at how this looks with variables. So with variables, it's the same idea. We calculate the LCD first, or lowest common denominator. So we're looking at the LCD between x minus 1 and x subtract 2. Since these do not have any common factors, the lowest common denominator is simply their product. Now you can multiply on the left or you can multiply on the right. Since I have room on the right, I'll go ahead and do it there. So I'm multiplying by x minus 1 over x minus 2 all over 1 over x minus 1, x minus 2 over 1. Notice I've drawn one of my fraction bars larger here, and that should line up with the big fraction bar there. Now look at your numerator, and by numerator I mean above the big fraction bar, as its own problem. And notice that there is a factor of x subtract 1 in the numerator and the denominator, that I can cancel. Now look at your denominator. There is a factor of x subtract 2 in the numerator of the denominator, and then the denominator of the denominator that I can cancel. We want to make sure that we simplify before we multiply. So this would turn out to be an absolute disaster if you tried to multiply x plus 2 by x minus 1 times x minus 2 and divide that by x subtract 1. The whole idea behind this method is you're multiplying by something that you guarantee will get rid of the complex nature of these fractions. Now this is a different kind of complex than complex numbers, but what makes this a complex fraction is the presence of a denominator in my numerator and a denominator in my denominator. And what we're trying to do is get rid of that. So my answer is just the product of what's left in the numerators, which is x plus 2, x subtract 2. They have a denominator of 1, so I don't need to write that, over x plus 4, x subtract 1. And we should take note of the cancellations we've made. So x cannot equal 1 or negative 2. Those are from my canceled factors. And if the problem asked you to list all domain restrictions, then we should also say that x could not equal negative 4, and that is from what ends up being a denominator here, which was a numerator there. We already took care of the fact that x could not equal 2. Oops, sorry, that should have said positive 2, not negative 2. I canceled a factor of x subtract 2, so x could not equal positive 2. So fix that. Oh, it won't let me erase that, so I'll just say that. Let's just double check everything. So I couldn't have a 1 because that would have been a 0 in the denominator of the numerator, and I canceled that factor. I cannot have a 2 because that would have been a 0 in the denominator of the denominator, and I canceled that. And then I also cannot have negative 4 because that would create a 0 in the numerator of the denominator, which eventually ends up being a denominator. And then I also can't have x equaling 1, but we already took care of that when we wrote our canceled factor. So there are more to these set of notes. There's another method that we're going to discuss, creatively called method 2, but I'm going to address that in another video.